so much for coming. I would like to go and introduce real quick Heather Gall. She's an assistant professor who is going to discuss our EDC footprints.
Okay. Well, thank you so much for having me here. It's really a pleasure to get a chance to talk to you. I've given this talk a few times now, so I think that's one of the reasons why we're going ahead and recording it, is so that way I can reduce the number of times that I'm giving the seminar across campus. But I'm really thrilled that there's so much excitement about it. And just a little bit of background, I do serve on our department's green team, so all of you are green team members, is that true? No? Oh, okay. That's what I was under the impression that that was the case. But anyway, it's really awesome to get a chance to talk with you today. If you have any questions as I'm going through my presentation, feel free to stop me. I'm more than happy to entertain questions as I move through it. And so I thought, given the topic that we're going to be talking about today, that it might be useful to sort of just give you a brief overview of sort of the history of water regulations in our country. And so we first started regulating surface water bodies back in the late 1800s, and the purpose of that was actually to make them navigable. So we wanted to be able to use our harbors and our rivers for navigation-related activities for trading. And so this was mostly associated with dredging those rivers and harbors, and that means just taking the sediments out if they accumulate so that there's space for the boats to navigate safely. And then we started looking at discharge of human waste. So we had modern septic systems and wastewater treatment plants today, but that was not always the case. And so this was first regulated at the state level in the early 1900s, and then began being regulated at the federal level in the mid-1900s with the Federal Water Pollution Control Act. And so clearly that wasn't sufficient for making sure that we had clean, safe water for us to drink and recreate in. Sort of the smoking gun that led to the creation ultimately of the EPA was the burning of the Cuyahoga River in Ohio. So I'm not sure if any of you have heard of that happening. But this was in 1969, and there was so much industrial waste in the Cuyahoga River that it actually caught on fire. And so when your rivers catch on fire, that probably is a good indication that something is wrong. And so this led to ultimately to the creation of the EPA in 1970. And so then we had the Clean Water Act in 1972, and it had some pretty bold goals of reducing many different types of pollutions into our surface water bodies, and to basically to eliminate toxic discharges so that we could have water that would be safe to fish in and to recreate in. And can anybody think why we might need this at the federal level? Why might state level regulations have been insufficient? What is it about water by nature that makes it an interstate issue?
Rural rivers cross state boundaries.
Exactly. So yeah, most people generally tend to know that answer. So it's an interstate resource, so it makes sense that we need to regulate at the federal level. And so if you think about the Chesapeake Bay and all we're trying to do to protect and restore the bay, clearly there are many states that are contributing to that problem. And so it takes the EPA at the federal level then to create the legislation then that allows us to improve the water quality. And so when we think about standards for water, it sort of depends on what that water's purpose and use is. And so we have more stringent regulations for drinking water than we do if we're recreating in it or fishing, or if we're restoring something for a specific habitat purpose for an endangered species perhaps. And even with all these regulations though, we're still facing issues, of course, across our country. And so this is a map of sort of the threatened or impaired waterways based on whatever the recreational or drinking water purpose is. So however that water body is supposed to be used, if the drinking water standards or whatever standards for that particular end use are exceeded, then let's see if I can get this thing to work. Then you have a redder or a dark brown color. And so I actually grew up in New Jersey, and so you can maybe see why I started to become very passionate about our water. There's a lot of water issues in the state of New Jersey. And so our modern drinking water standards actually went into effect in 1977, but they haven't really been updated that much since the early 90s. And so we have these primary drinking water standards. They're regulated compound by compound, and so if you look at the usually annually, your drinking water company will give you a report to make sure that you know that the water that you've been drinking has been safe, and if there's any exceedances, they're required to let you know. So that's true for what we call primary drinking water standards, but there's also secondary drinking water standards, and these are for things related to how the water looks, aesthetics, or how it might smell. And so they're not necessarily health related, but they might make the water undesirable to drink if those secondary water standards are exceeded. So your drinking water treatment plant is required to meet primary, but only recommended to meet these secondary drinking water standards. And over the past maybe 10 or 15 years or so, they've started to create this contaminant candidate list. And that's sort of where my emerging area of research around these endocrine disrupting compounds and what we call emerging contaminants comes into play. And so we're starting to see pharmaceuticals and personal care products and estrogens in the environment at very low levels, and because they can have endocrine disrupting effects, they're on this contaminant candidate list to eventually become regulated. So we don't know enough about them to regulate them yet, but that's the goal, is to ultimately get them regulated. And so what are these emerging contaminants? So they're basically generally chemicals that are found in the environment at very low concentrations, so very trace level, much smaller than most of the drinking water standards are for some of the things that are on that primary drinking water list. And they typically don't have, they're not generally things that we sample for in the environment because they're not regulated. So they're often things that we're just becoming aware of. Even though they may have been in the environment for a long period of time, we're sort of just becoming aware of their presence in the environment. And so these are things that are found in products that we use every day. So if you did laundry recently, again, you were releasing some of these emerging contaminants in the environment, maybe inadvertently, but and then household cleaners and health and beauty care, personal care products all contain some of the ingredients that we would refer to in the environment as emerging contaminants. And so basically, I get a lot of questions, especially, yes?
I saw a cup of coffee there.
Yes, so caffeine. Caffeine is indicative of wastewater. So if you see that in the environment, it's likely because you've had a release of wastewater. It passes through you after you've drinking it and winds up actually going somewhat through the wastewater treatment plant. So our wastewater treatment plants aren't required to remove these things, so that there's no wastewater standards for these. And so they wind up in the environment. It's just like it causes behavioral changes for us at low levels in the environment, it could also potentially cause low-level behavior changes in non-target organisms as well. I wouldn't discourage you necessarily from drinking caffeine. It is a natural ingredient, so it does break down in the environment, but it is one of the things that's on the list of emerging contaminants. So I talked a little bit about these trace levels, and one of the questions that I get is, okay, well, what does it mean to have a nanogram per liter level? It's a very low concentration. So a nanogram is 10 to the minus 9 grams. And if you think about what a gram is, you can think about like a grain of sand or a paper clip. And so I just kind of did a back of the envelope type calculation to try to explain what that means. And so if you took a football field and basically stacked 10 single-story houses high and filled that with water, then that would be 10 to the 9 liters. And so then if you put a paper clip into that water, which has a mass of 1 gram, then that concentration of that paper clip and that massive amount of water would be 10 to the minus 9, so not nanograms per liter level. And so that's how to think about the levels at which these emerging contaminants are active in the environment. Okay, so we talked a little bit about the sources of these emerging contaminants. So if they're things that we're using in our everyday lives, they wind up in our wastewater stream. So after we shower, after we flush the toilet, however we're using them in our household, they wind up in our wastewater treatment plants. The treatment plants don't necessarily have to remove these contaminants, so they can be released into surface water bodies as that wastewater treatment plant, that treated effluent, is being discharged back into our rivers. In some cases, we might have combined sewer overflow events, and I'll go over what those are in a moment. But that's actually the release of raw sewage into the environment, and so many old cities have these combined sewer pipes that are carrying both stormwater and sewage. And so if you're during a rainfall event, sometimes those systems can become overwhelmed, and there's not enough capacity to actually treat that amount of water. And so these pipe systems actually wind up diverting water from the treatment plants and directly discharge it into receiving water bodies. And so then you basically have untreated waste getting discharged. And there's a lot of efforts now to remove these combined sewer systems, but they still do exist for the time being. And another source of these emerging contaminants is concentrated animal feeding operations. And so if you think about how animals are raised in these systems, they're in very close proximity to each other. And so if one of those animals were to get sick, then you would have a spread of disease quite rapidly through those concentrated animal feeding operations. And so they're often given low levels of antibiotics then consistently to make sure that the spread of disease is low. And so that can actually lead to the discharge then of pharmaceuticals from these sources into the environment. So lots of times we're using the waste that those animals generate as a fertilizer. So we're applying that in either solid or liquid form to our agricultural systems. And then so during rainstorm events, you can actually get runoff from those fields that's carrying that directly into the receiving water bodies. And so just to give you a little bit of perspective on the scope of these concentrated animal feeding operations in the US, so this is a map of their density. The brighter the red, the higher the density of these facilities. This one's showing all different kinds of animal feeding operations. You can also use this map to just look at cattle, dairy, hogs, broilers, and layers, chickens. And you can see sort of in the southeastern part of Pennsylvania, we tend to have a high amount of these concentrated animal feeding operations. And so that actually turns out to be a pretty significant source of nutrients, as well as other contaminants into the Chesapeake Bay. And so there's a lot of work being done right now to try to figure out how to cope with those issues in the southeastern part of the state. And for combined sewer overflow systems, or combined sewer systems, they tend to be in older cities across the United States. And so very prevalent on the East Coast and also a bit on the West Coast, but not so much in the central United States. So predominantly those were installed back in the 1800s or early 1900s before we really thought to have those be separate systems. And so how many of you have heard of pharmaceuticals in the environment or in your drinking water? Is that something some of you are aware of? Okay. So I guess one of the ways you can discover that the general public is becoming aware of something that you're doing in your research is with cartoons. If you see cartoons that are sort of emphasizing your research area in the newspaper, you say, oh, okay, maybe this is something the general public is starting to learn about. And so this is just a sort of a joke that says, since the pharmacy is closed, the doctor said you should have 3 glasses of water. And there's this little newspaper clipping that says pharmaceuticals are in our tap water. And so it's just kind of a nice indicator that this is something that the general public is becoming increasingly aware of and concerned about. And then I think in 2012, forget the exact date on this AP story, but they actually looked at major drinking water supplies across the US in big cities. So Philadelphia was one of the water supplies that they tested, and if there's a red dot, that means at least one pharmaceutical was found in that drinking water supply. This doesn't tell you the levels at which they were found, but red means they had at least one hit. And then the gray would mean that it wasn't tested for pharmaceuticals, and green would mean that it was tested negative. So not so many green dots, certainly more red dots than green dots across the US. And so a common question then is, should you worry? If this is in your drinking water, do you need to be worried about what this might be doing to you? And so from a human health perspective, the EPA recommends an intake of about 2 liters of water per day. And so this is just a suite of different pharmaceuticals and their associated dose in milligrams. And so based on the concentrations that these different pharmaceuticals are found in the drinking water supplies, this is the number of liters you would need to drink of that drinking water in order to get 1 dose of that pharmaceutical. And so if we're talking about hundreds of thousands of liters or more than 1 million liters of water, you might not think that this is a significant issue for human populations. And so that might be generally true, but when we think about people who might be immunocompromised or young infants who might be exposed to this, or pregnant women, there are questions around the safety associated with consuming even low levels of these in the environment. And there can also be interesting interactions among different kinds of pharmaceuticals and emerging contaminants. And so if they're being used in the same way to treat something in a common method, then they can actually kind of combine together in these interesting synergistic ways, and their effects can be more than what you would expect them to be if you were just to add the effects of them separately together. And so there's some interesting toxicology questions around what it means to have multiple of these emerging contaminants in the same drinking water supply. And when you think about how the EPA currently regulates drinking water, it's compound by compound. And there's some suggestions that that might not be sufficient for us to sort of get a handle on the emerging contaminants issue. If multiple compounds are causing the same effect, then maybe we need to regulate the effect instead of the individual compound. And so there's just some interesting work being done around that. Okay, so maybe it's not so much of a problem from a human health perspective, at least for the general population, but what about our aquatic ecosystems? And so these would be where fish and amphibians may be exposed to these compounds more consistently. And so this is just another cartoon that's showing a fish that's being exposed to whatever is in that combined sewer system. So both garbage and pharmaceuticals and maybe pesticides or something like that. And so there have been a lot of exposure studies done in the lab and also observed in the field that are starting to see either masculinized female fish or feminized male fish. And so if any of you have seen some information that's come out recently from the Susquehanna River Basin, there is a lot of concern around intersex characteristics in our smallmouth bass population. Something like 90% of our smallmouth bass male populations are showing indicators that they have eggs inside of them. And so clearly that's a problem, and it's being linked back partly to these emerging contaminants, but also a lot back to pesticides that can also have feminizing effects. And then you can also see these have all sorts of implications for abnormal hind limb development in amphibians. And so these sensitive aquatic organisms can have effects at environmentally relevant concentrations of these compounds. And sort of just to give you a perspective on what we see across Pennsylvania, there was a study done by the U.S. Geological Survey in 2012. So this is summarizing concentrations and detections of different pharmaceuticals and personal care products in the environment across Pennsylvania from 2006 to 2009. And so basically they looked for places where they might expect there to be an impact, either from concentrated animal feeding operations, runoff from agricultural fields, streams that were receiving municipal wastewater effluent, streams that are used for drinking water sources, or streams that are used as indicators of fish health. And so they have identified various locations across the sort of southeastern part of the state to sample for impacts from animal feeding operations. And then across the state, each one of these orangish dots is one of their sampling locations related back to fish health or drinking water intakes. And so some of the things that they looked for are what they call these organic wastewater contaminants. And so these would be compounds that are passing through the wastewater treatment plant that have human origin. And so, or potentially veterinary as well, so I'll talk about that in a second. So natural hormones is something that they looked for. So this is something we all excrete naturally, and so that does wind up bypassing through a wastewater treatment plant and into receiving water bodies. And so, of course, humans produce these, but animals do as well. And so we see these natural hormones from both animal and human sources. So medications, both human and veterinary medications. So I talked a little bit about the use of antibiotics in concentrated animal feeding operations. And so you might see veterinary medications winding up in the receiving water bodies, both prescription and over-the-counter drugs from a human health perspective. And then household products. So detergents, fragrances, flavors, lots of things that we use to enhance the quality of our lives can wind up into the environment as well. And so they have designed their experiment to look at the effects of upstream and downstream locations relative to things that they think might be sources. And so animal feeding operations, that's this APHOS. So the left side of your screen is the number of hits that they saw for various pharmaceutical compounds upstream of an animal feeding operation, and then this side is downstream of animal feeding operations. And so you can see they maybe had 1, 2, 3, or 4 hits of these pharmaceuticals upstream, and the number of hits downstream increased a little bit. So maybe they went to have it from 1 or 2 to 3 or 4 hits that they were getting for these different pharmaceuticals. But what about wastewater treatment plants? And so this is basically the same kind of graph, but now we're looking at upstream of wastewater treatment plant sites and downstream. And so the number of hits goes up significantly downstream of wastewater treatment plants. And so it's a pretty good indicator that humans are a big source of these. Yes?
Just because I can't read what those are on the bottom, could you just mention a couple of them that are notable to you?
Sure, so there's some painkillers, so acetaminophen is on here, caffeine is on here, some prescriptions, medications related to antibiotic use, or an epilepsy drug is on here. So these aren't necessarily things we would recommend that people not take, right? I mean, these are things that we sort of rely on for modern day health. But it is an indicator that they are relatively absent upstream of a human wastewater source, but then downstream of that source we do see it. And this is treated effluent that's being discharged into the receiving body. So it's an indicator that they're persisting through that treatment plant process. And then the red, so these different colors, when you think about how these are being detected analytically with the instruments that we have, there are different levels at which we deem acceptable to detect these. And so the blue would mean that we were actually able to give the concentration in number, and the red means that we see it, but we don't have enough confidence in the level at which we're seeing it to actually assign a concentration to it. So you can just kind of think of that as a positive hit, whereas these blue bars were numbers we were actually able to quantify for the concentration in that. And so then if we look at the different kinds of endocrine disrupting compounds or emerging contaminants, so this again are different sampling sites across the state, the number of hits, and then the different bars are sort of showing the contributions. The pink is from pharmaceuticals, except antibiotics, the green is antibiotics. The yellow is hormones, and then the orange are these organic wastewater contaminants, which are basically coming from our personal care products. And so if you look at this, you can kind of see that the dominant contributor for the most part across these sites are these organic wastewater compounds. And so when we think about ways that we can reduce them in the environment, if prescription medications aren't necessarily the biggest contributor to the problem, and if it turns out that it's things that we're using in our everyday lives, then that sort of comes back to sort of what are the low-hanging fruit for reducing their presence in the environment. And so if we know that we're seeing these chemicals in the environment, because there's no standards necessarily for wastewater treatment plants to reduce them to, there's no drinking water standard, so they wind up in our drinking water. They persist in the wastewater effluent, and they're found in surface water bodies not just across Pennsylvania or across the U.S., but across the world as well, particularly downstream of wastewater treatment plants. And so we think that maybe one of the best ways we can reduce them now in the environment is actually just to reduce their source. So how can we increase awareness of what the sources of these problems are and give people tools that they can use to maybe make informed choices in what they're using in their everyday lives. And so it's sort of inspired by that vision, we set out back, I guess in the summer of 2014, we started working on this EDC footprint calculator. And so have any of you used like a water footprint tool or a carbon footprint tool before or heard of something like that? Okay, good, most of you are nodding. So we were sort of inspired by that idea to develop this EDC footprint tool. So you basically answer a series of questions on the kinds of products that you own, and in the end it'll spit out a mass for you of what your footprint is. And what's kind of most exciting for me about this project is it was actually entirely done by undergraduate students. So I've had 3 undergraduate students that have come through my lab, one that started on this in the summer of 2014, and then we had 2 in the summer of 2015 that worked on it again, and we sort of completed our first version of it that fall, and then we sort of more broadly launched it just at the end of last year. We wanted to get our documentation together to be able to share, so that people didn't just have the tool, but they had some information they could actually have accompanying them with that. And so we published a conference paper over the summer, and then launched this officially at the end of last year. And so what this basically looks like, if you were to download it, this is the interface. It's basically an Excel spreadsheet that you can download. And there's 3 different product categories. So your cleaners, household cleaners, laundry detergents and laundry related items, and then health and beauty products. And so basically what you do is you fill out the mass or volume, depending on whether it's a solid or liquid, of each of these products that you have. And then this is sort of where the undergraduate students spent all of their time figuring out what numbers need to go in each of those boxes. And so this is a suite of different classes of endocrine disrupting compounds, and each one of these boxes has a concentration associated with how much of each of these are in each product. And so in the end, then it can give you a number on what your footprint is. And so sort of the power behind this, there was a study that was launched from the Silent Spring Institute in 2012 that was looking at a bunch of different personal care products or household products to try to quantify how much of these emerging contaminants are in each of them. And so, for example, they would take 10 different brands of toothpaste and combine them together into a representative sample and analyze that, and then figure out which of these compounds were in that toothpaste. And so you can't necessarily say, I have Colgate whitening toothpaste, and it'll give you a number, but it'll give you a general number for toothpaste. At least that's where we're at right now. And so if you look at the numbers, the higher the red, or the more intense the red or the brown, the higher the concentration. But there's actually a very broad range that was reported in this report. And they didn't actually have like the raw numbers associated with it. So the biggest range then is just greater than 1,000 micrograms per gram. And so we didn't know, based on that, what to put into our calculator. And so for the rest of the ranges, we just used the average. And so there's going to be error associated with the number that we're producing, but at least it gives you some sort of a reasonable representation of what you might expect in your products. But for that number that's just greater than 1,000 micrograms per gram, we really couldn't put a number on that with just this study. And so we started looking on where we might be able to get more information. And I don't know if any of you are familiar with this website. I wasn't until I started doing this project. But the U.S. Department of Health and Human Services actually has this database where you can basically look at everything that's in any product that you have in your house. And so this could be for poison control related issues. If your dog or your child accidentally consumes something, well, you want to know more about what's in it or how to respond. Then you can come here and then look up whatever it is that they consumed and figure out what was in it. Or for people who have allergies, if they need to avoid a certain ingredient, they can use this website. And so we decided to sort of mine this then for that additional information of levels that were above the biggest number in the previous report that I described. And so you can come here and see the personal care products tab and then inside the home, and so those would be the two places where we were looking for more data. And so just an example of how we use this, so if you owned an antibacterial soap, the specific one style, and there are different percentages for various ingredients, some of which we're using in our calculator. So triclosan is the active ingredient in most antibiotic hand soaps, and it's actually being phased out starting this year in 2017. So this is something that we have included in our calculator, and here we would be able to get the percentage of that particular ingredient that's in these products. And so we sort of pretended we were combining different brands together and got an average then to feed it into our calculator, sort of mimicking what the Dodson et al. Study from Silent Spring Institute had done. And so that was a way for us to get numbers to put into the calculator for items that had concentrations above that biggest threshold. Okay, so what actually is it that we have in our calculator then? So there's these 8 different categories. I believe that's 8, maybe it's more. But sunscreens, and then a bunch of different things that are in our personal care products. So solvents and cleaners are these glycol ethers, siloxanes are in silicones or anti-foaming agents that are used in our detergents. Fragrances, so this is a picture of dryer sheets, I know that might be hard to see. And then alkylphenols, which are in our surfactants, detergents, and other cleaning products. Ethanolamines, which are in our glass cleaners and laundry detergents. Antimicrobials like triclosan, that's actually the main one, and it's metabolite, we also look at that. BPA, so that's probably the most commonly known of these emerging contaminants in the environment, and people are very well aware of that. Many of you have reusable bottles that you're using right now, probably to help reduce the BPA that you have in the water that you're drinking throughout the day. And then phthalates and parabens, if any of you are looking at your personal care products or maybe makeup or shampoos and conditioners, things like that, a lot of them tout being phthalate or paraben free. And so that's just one of the ways that we're sort of trying to reduce the presence of these in the environment, because we know that they can cause these issues after we use them. Okay, and so then what does this all look like inside of our calculator? So these are those different categories of contaminants or contaminant classes and different items that you might have in your household. So these range from surface cleaners, floor cleaners, glass cleaners, air fresheners, down to liquid dish soap. So these are just different items you might have. And then you can see fragrances, alkylphenols, and phthalates are sort of some of the dominant chemicals that are in many of those products. Same thing holds true for laundry products. So laundry bleach, laundry detergent, and dryer sheets are the 3 products that we survey for here. And again, fragrances, alkylphenols, and phthalates are present in most of those items. And then health and beauty products is our longest list. And so this would have everything in it from soaps, shampoos, conditioner, shaving cream, body lotion, and makeup. And so you would just enter the amount of each of these products that you have. Fragrances, of course, is in almost every single one of these. Nobody wants to use a body product that doesn't smell good, so most of them have fragrances. Alkylphenols, some have antimicrobials, BPA, phthalates, and parabens as well. So just a suite of different chemicals that are in these products that we're using. And so the way that our calculator works then is it gives you pie charts in the end that you can sort of use to help make decisions about ways to reduce your footprint. And so I had a student and myself, so family A and family B, that took this survey that use this tool to provide some example output. And so you can see for family A that laundry products were the biggest contributor to the total footprint, and for family B, health and beauty products were the biggest contributor. And so we had different total footprints. Family A has 5 people and is from Long Island, and family B has 3 people and is from locally. And so then we can look at the contribution of each of the chemical categories to our total footprint. And so for the first family, so it looks like ethanolamines and maybe fragrances were the biggest contributors. And for family B, it looks like glycol ethers and ethanolamines were the biggest contributors. And so this sort of gives you an idea of what your portfolio of your footprint looks like. But probably the most useful and of interest is that it actually will rank the top 10 products that are the contributors to your footprint. And for both family A and family B, that turned out to be laundry detergent. And so if you wanted to think about ways to reduce your footprint, then you could maybe go to the grocery store and look for plant-based laundry detergent instead of whatever it is you're typically buying that may have more synthetic chemicals in it. And so we're not making specific recommendations, but this is just supposed to be a general way that people can think about ways to strategically reduce their footprints. And some ways to think about how we interpret the results. So if you looked at these numbers, right, these are grams. So how do you convince somebody that 200 or 100 grams of chemical is bad? I mean, that's a very small amount that might be in all of your household items. But again, remember, we are talking about these things being active in the environment at 1 nanogram per liter level. And so that the fact that we're many orders of magnitude higher than that in our footprint then could potentially be an issue. And so basically what we're trying to do is take that really small number and try to scale it up to give people a visual way of thinking about what that mass is. And so basically we take that footprint and divide it by the number of people that are in that household, so we get a per capita mass. And then scale that up by the number of people in the US, so roughly 318 million. And then basically convert that mass to a mass of a commercial airplane. And so families A footprint then, if everybody in the US had the same footprint, would be roughly 40 of these commercial airplanes, and family B would be roughly 32. And so another way to think about that could be what it might look like if you were to take that mass and potentially dump that into the Chesapeake Bay. So of course we're representing what's in your household products before it goes through wastewater treatment plants, so this is really not representative of what actually makes it to the environment. But still, if your footprint is 10 to 15 milligrams per liter, or if that's what your footprint times the number of people in the Chesapeake Bay divided by the volume of the Chesapeake Bay's water, actually turns out to be roughly 3 to 6 orders of magnitude higher than what we know affects aquatic ecosystems. And so it's just another way to think about those results. And so right now, this Excel footprint calculator is available to download. One of the disadvantages of it is that it doesn't give us any information back, and it doesn't allow you to see how you compare to other users. So it's sort of just a one-way Excel tool that you download, and then it's on your computer, and what you choose to do with it is sort of up to you. And we're in the process now of turning that into an online survey tool. I just wanted to sort of mention, this really hasn't cost us any money to do so far. The students that worked on it all brought in funding from various sources across campus or through this off-campus Summer Research Opportunities Program, which brings students from other universities to Penn State to do research over the summer. And we did work with Penn State's extension group in the College of Ag. So Brian Swistock is our water resources group, and we wanted to have a way to put this onto a more publicly accessible website. If it's just on my research website, nobody's really going to find it. And so we wanted a way for it to be more broadly available. And so we worked a lot with Extension then to help us be able to do that. And then sort of the big story broke at the end of last year. I don't know how many of you saw this in Penn State's news. But basically, the College of Ag decided to do a story on this, and I think they were most excited not just because of the content, but because it was done by undergraduate students. And so that was one of the big selling points for this was, wow, look at this cool thing that a couple of undergrads at Penn State worked on during their summer months. And so it's been really fun to watch this take off and to see my students' faces light up. Those who have graduated still see my Facebook feed and follow what's going on with this. So it's been a lot of fun to keep the inspiration going with this project. And right now I have a postdoctoral research associate in our department sort of working part-time in my group. She's also working part-time with another group in our department to turn this into an online survey. And so this is released now, but we're still working through kinks. But basically you can go to sites.psu.edu/EDC calculator and access either the Excel version or this online survey tool. And so the Qualtrics tool then is the online survey version. So if you just go to calculator, you can see the two different versions of it. And it's basically the same thing, but just two different ways of accessing it. And so this is what it looks like if you start scrolling through the survey. It's estimated that it'll take 20 minutes to complete if you already have sort of all your stuff gathered, and all you have to do is enter the masses or volumes. And then you say how many people you have in your household. And then enter the masses or volumes of your surface cleaners, and then of your laundry items, and then of your personal care products. So basically those same three categories that we have in the Excel version. And then in the end, it'll give you information about the contribution of each of those to your total footprint and your total footprint. So right now everything just says 0 because I just wanted to show you what it looked like. And again, we're doing this scale up to the size of the commercial airplanes and the number of commercial airplanes that your footprint would be. And so what we're trying to do then is take this and ultimately turn it into a smartphone app. So I'm working on writing a grant right now to hopefully be able to do that. And sort of our vision is that it's really difficult for consumers to make informed choices while they're shopping. So especially for things that you're not ingesting, product labels can be really confusing. And so especially cleansers, which you're not putting on your skin, don't even have to reveal all their inactive ingredients. And so a lot of things like fragrances or other things that might be on this emerging contaminants list don't even have to be on that label. And so how can you as a consumer make informed choices about what it is that you want to buy if you want to reduce your footprint? So what we'd like to do is ultimately have this app that connects back to that household database that I showed you. And basically you can scan different products and maybe it'll make a recommendation on what the lowest footprint would be. So that's sort of our idea for that. We would also like to use this as a research tool. So the university has this unique setting where all the wastewater generated from the university goes to a university-operated wastewater treatment plant. And so if we can survey a cross-section of students and people who are on campus, we might be able to predict what the wastewater treatment plant would expect to see coming to the treatment plant. And so I serve on the wastewater treatment plant sort of advisory committee, and so there is interest in the treatment plant operators to have that information. So we might be able to use it as a research tool in that way. I also think there's some interesting social science related questions. If you think about socioeconomic classes or majors on campus or all sorts of other variables, we might be able to sort of look at how different footprints vary as a cross-section of people or where they're located as well. So if any of you are familiar with sort of food desert issues in cities, so where people have access to shopping nearby, if you want to reduce your footprint, it might be a lot easier to do if you have a Trader Joe's or a Whole Foods down the road, but if your shopping options are limited, then that might be driving why your footprint may or may not be higher. And so there are some questions we'd like to do around that. And most importantly though, I think it's to have fun and to aid everybody to be better citizen scientists and to be thinking about ways that their personal actions every day impact our environment. And so a lot of people are thinking about these things from a drinking water perspective, but they might not link that necessarily back to items that they use every day. And so just to have a way that people can, who would like to make more informed decisions about reducing their footprint are able to do that. And so those are sort of our broad goals. And with that, here are the websites that you can use to access our footprint tool and my email address if any of you have any questions. But thank you for listening. I appreciate it.
When you enter information, is that volume per year?
Yeah, so a lot of these footprint tools have a time component associated with them, right? But this one really doesn't right now, and that might be something we're ultimately able to get to, but then we would have to estimate like how much toothpaste people are using per day or something like that, or how long it would take them to use a stick of deodorant. So I think the time component right now is a bit harder for us to get at. So right now it's just a snapshot. So whatever you own at the moment is what would be represented in your footprint tool. So if you go home and open your laundry cabinets and your personal care products cabinets and enter, it's just representative of what your household footprint is right now.
I see.
Yeah, so there's no time component associated with it. It's more just a snapshot. So if you just went
it's
to
before I go shopping.
yes,
or after,
right,
it doesn't
exactly. So if
matter.
you just stocked up on something from Costco, then your footprint tool might be a lot higher, even though it's going to take you maybe a year to use all of those products. So if you wanted to think about from your own personal perspective a time frame that you're interested in quantifying, and then you could think, okay, well, over the next month or so, what would I be using, and reflect that in your calculation. But right now, there's no time component to it. So hopefully we can get there. We thought about it, but I think to keep the undergraduate students from drowning too much in this, we decided not to take it quite that far, but it is, I do think we'd like to get there ultimately. Yeah.
Is the source of human pharmaceuticals in a waterway, is that improper disposable of excess or
It's a great
pass
question.
through the system?
It's both. So I think as people become more aware of how to properly dispose, there's less flushing. I'm sure some of it is still flushing. I haven't seen any reports that have quantified contributions from one particular activity, whether it's excretion versus improper disposal. I do know the disposal issue can become problematic because if you're to do a collection somewhere requires a police officer there. And so just organizing those, I think that townships try to do them, but they're maybe once a month.
We collect all the time at Bellefonte.
Bellefonte, okay.
An officer told us that.
Oh, that's really good to know.
And I remember reading somewhere that I thought State College was going to start too, and it's just inside their.
Inside the police department, okay. That's really
Bellefonte
good.
does all the time.
Okay, yeah, good.
But are any pharmaceuticals, basically, if somebody takes it, that through biological processes, they come out in a safe manner, or?
Yeah, so some of it is not absorbed. So you do release a fraction of the active ingredients.
Okay.
And there's also the biochemistry of these is such that even if the parent compound breaks down, the metabolite can still be active to some extent. And so we traditionally think of, okay, if you get rid of the main compound, then you've gotten rid of the problem. But for these pharmaceuticals, that's not necessarily the case. And so there's also a lot of interesting work. We have to identify all the breakdown components as well. And so that's not all known yet for all of these parent compounds, if that makes sense.
Do you know what's done with the captured pharmaceuticals?
Incinerated. It's incinerated.
They're incinerated.
Yeah.
You know, there's scrubbers on that. I mean, it's either just sort of displacing the problem or what?
At least what I've heard is that it's usually done in the same places where pets get cremated. I don't know if that's true or not for here, but that's at least what I've heard. So I don't. Maybe some places have whatever would be necessary for these.
So it's a
specific
specialized
kinds of compounds,
incineration. Something.
Yeah. I know
Yeah.
it's incinerated. I don't know in all cases how that incineration is done or what proper controls on the air emissions for that might be.
Yeah.
Yeah, or even what's done with the ashes. Not really sure.
Right. With some, right.
Right. Anything else? Are you all gonna go take the footprint tool now?
So I don't want to dominate, but I had some other questions, but I'll be quiet.
Oh, I don't mind. Go ahead.
Are you familiar with, or anyone here familiar with Good Guide?
No.
So there's an app. I don't know to what extent it's very similar. It seems like, but you could even on your phones right now go to Good Guide. So I've used it. You can scan a barcode. It's health and beauty product. It's very similar to what you're talking about.
Oh, great.
And they claim to have, I have it on my phone, 250,000 products. They raised about $10 million of private equity. This is a guy that was at MIT, now at Berkeley, Dara O'Rourke. And what they started with initially was very ambitious, and I remember using this tool with students years ago, and it would actually give you a lot of times you scan a product and it would say, we haven't done this one yet, but when you found a product like, Suave shampoo, it would give you an environment score, you get a human health score, an environment score, and sort of a social score, which I think had something to do with like supply chain and sort of worker,
Yeah, sure.
workers. And
That's
all that.
awesome.
But now they've changed it. I think they realized it was too ambitious. So, in fact, just last night, because my wife is a sociologist and teaches in biobehavioral health, and teaches right now an environmental health class. She's not a, well, she's a social, I shouldn't say she's not a scientist, she's not a natural scientist. So she doesn't touch so much on the depth of sort of the technical, the science part of it. But we were looking at it just last night, and it only looks at human health now. So it seems to map very closely to what you're talking
Yeah,
about.
let's
They would-
take a look at it.
Yeah.
Yeah,
So
that's
yeah,
great.
so yeah, Good Guide is pretty cool, and you can click on things and kind of drill down into the ingredients, and I don't know what's behind it, but they do share their methodology. It seems to be somewhat open source, and you can look at different ingredients, and they have some way of scoring the ones that are of low and medium and high concern, and
That's great.
that kind of thing.
That might reduce the amount of work that we have to do on our end then, if there's
Yeah,
already a
right.
tool that's very similar, so that's great. Yeah, even if there was a way, if you wanted to do your footprint of your own products and could just sort of use your phone to scan what you already own, that would be really useful, so that you didn't have to go into the tool and enter all of that yourself. So I think there are some things we'd like to do with mobile technology, even if it isn't ultimately a consumer recommendation. And we have to be careful too, from Penn State, we don't want to be advocating for certain brands, so
Right.
there's a little bit of touchiness to that.
Yeah.
So we just have to kind of see where this leads, but
Yeah.
this is where we're at so far, and we'll see where it goes from here.
Well, I know the one thing that Good Guide doesn't have is it's not a footprint tool.
Right.
It's really sort of product by product, So it would be interesting if you could scan something in your house and actually enter an amount, and then it would give you because that's very interesting. And I haven't seen anybody that is doing a footprint calculator for endocrine disruption.
And I was quite surprised that was the case. When I first had this idea, I was like, well, somebody must have already done it, and then sure enough, they hadn't. So we were pretty excited.
And do you do any work with sort of the? I'm thinking about the people who are actually designing the chemicals, kind of in the from a product development sort of chemical engineering perspective. So I have a good friend who's a chemical engineer. Is there any work being done to kind of get this upstream so that we actually just design these things out of product?
And there's a lot more being done with that now on the pharmaceutical side as well. So how can we design drugs to be more environmentally friendly so that when people use them and they bypass some percentage of them bypasses through us, that they degrade safely in the environment. So I've not collaborated directly with people who are doing that kind of work, but I think it's better understood for the I guess for the household product side than it is for the pharmaceutical side. So it'll be interesting to see how that goes. I know there's a lot more efforts now for our campus to collaborate with Hershey Medical Center. And so I have started conversations with toxicologists on campus, but we haven't yet put anything together yet.
Yeah.
I've only been here for 3.5 years, so so hopefully.
Because your area what is your area?
I'm actually an environmental engineer by training, but I'm in ag and bioengineering, so I do more work on how these things are moving in the environment and how things like rainfall events move them, and designing from an agricultural perspective ways to reduce when they're leaving the field, like vegetated filter strips or green best management practices and things like that to help reduce their transport. So I deal with things on that end, not so much on the source reduction. So this has been our first more source reduction kind of perspective. And yeah, this is definitely different. At least this tool is very different than the traditional research that I'm doing.
Can you imagine one that's agriculturally focused, where a farmer gets because this is sort of household focused, and it'd be interesting to have one for agriculture.
Right, and I think that's mostly related to antibiotic usage. And so things, I mean, if you're giving all of your cattle low levels of a pharmaceutical, what might that impact be? And that's also being very driven now by antibiotic resistance genes that they're finding in the environment.
Right,
And so that's sort of more the angle that's driving that end of the research right now. And I do have a project that's going to start up this summer with Virginia Tech that's looking at antibiotic resistance related to dairy manure activities. So believe it or not, that tends to be more the traditional kind of work that I'm doing than this.
That's very interesting.
Sort of understanding what happens after those animal wastes are released into the field.
Well, last comment is, since this is a business school, I've got to also mention, so I teach class in sustainable business, and so I sort of track the news, and it just, in the last year, in fact, one of these was just last week, Target has come out and Walmart has come out with very sort of public commitments to, in their supply chain, make procurement decisions to eliminate chemicals of concern. I don't know everything that's on that list.
Mhm.
So it would seem to me that at some point there could be, interest from companies in a tool like this as
Yeah.
well.
Yeah, and I think, so the College of Ag has this RAIN grant program, which is sort of more looking at entrepreneurship opportunities, but I've been encouraged to submit this sort of smartphone idea
Oh, yeah.
in that direction. So that grant's due March 17th, so we're working on
Oh.
that in the next couple of weeks. So we are
You
thinking.
got lots of time.
Yeah, that's okay. It's a 5-page proposal, so not that it's easy to write that, but yeah. So we are looking at other non-research related avenues for this to ultimately go.
Yeah.
Mhm.
That's cool.
Yep. All right. Thank you.
Thank
Yeah,
you.
no problem. Thank you too. Thanks for videotaping.